All right, so let's get started. This is another stream. So I've actually been out for a bit, um, had to undergo a surgery. Um, so I haven't been streaming during that period of time. Now that I'm back, I'd like to continue to do that. So today, again, would just like to spend a couple of minutes on the stream and not taking too much time because I see that those are the most useful ones. So today we're moving from the whole candle series where I was trying to implement a transformer from scratch using the candle um, crate to now effectively taking another step, which is looking at LLVM. And for those who probably do not know about LLVM, like myself, um, because we don't work too much on the compiler. Uh, this should be a good start, like the basic stuff. Uh, I had a lot of time to do reading, so spent some time to learn this stuff. But effectively, what we're talking about is so far we've looked at trying to figure out how to work with the GPU, that's launching kernels, etc. But how does that process actually work? How do you take, you know, code that source code that you've written, and actually get it to run on, any kind of processor? It could be the CPU, it could be a GPU, a TPU, whatever it is. Any heterogeneous in a heterogeneous computing environment, how do you actually deploy that code onto a particular processor? So, well, there's not a lot of rocket science to that. You're going to need a compiler for that. And two of the biggest compiler projects today are GCC and LLVM. Of course, I think one's written in C, but LLVM is what I'm going to be talking about. It's pretty much, it's a C++ project. So that's the only gripe I have with it. And plus, had to learn a bit of C++ for this. But in any case, if we were to look at how you convert Rust all the way to assembly that runs on, let's say, a CPU to begin with, this is the flow. You'll see that you have your Rust source code, then it undergoes a number of transformations. All of these transformations can be considered, I'll get to what they are, they can be considered an intermediate representation of the same program that you've written in source format. So for example, if you were looking at, let's say, this simple program, which is, you've written a function that adds two numbers, that's about it. That's your source file. It undergoes all of these transformations and then it ends up in this place, which is called LLVM IR. I'll get to that part as well. But let's get to the first few pieces. AST, an abstract syntax tree. Now, I won't talk too much about this. This is basically you take your source code and convert it into tokens, and then you create a tree. And that's a hierarchical tree is what's created. Then there are a few other pieces that you would not see in other IRs, sorry, in other languages. You go straight from the AST and the older languages, you probably go straight from the AST into LLVM IR and then you do stuff with that. But here what we're doing is Rust has what's called a front end. So before it hands off your, uh, you know, before it hands off uh, to LLVMIR, or before it transforms itself into LLVMIR, it undergoes a bunch of different transformations, which we're not going to cover today. But that's essentially what the Rust front end is. HIR is what's called high level intermediate representation, very apt. And then there's THIR, which is the typed version of HIR. And then there's MIR, which is basically a control flow graph. You can look at all of this. We'll probably look at this separately, but I just wanted to keep it short. So we'll only look at LLVMIR. So when you get to LLVMIR, that's basically typed assembly. Now, with that flow, let's come to why we need to go through all of this. Because when you actually take your source code, the ultimate goal of you writing a piece of, code is so that, it can run on any one of these, you know, processors. It could be an x86 processor, or it could be an ARM processor, RISC-V, which is what the entire goal is over here. We're targeting RISC-V. So when we do get to that part, I'll show you how all of these things add up. And then MIPS, PowerPC, these are all different architectures or different ISAs, instruction set architectures. And you actually want to write your source code so that you could produce these machine instructions for these architectures. Now that process is what the entire compiler undertakes. So there's different parts to the compiler. It's not like the compiler is one monolithic piece of code that does everything and then gives you the appropriate machine instructions for your architecture. It goes through this process, which is C or C++ uses Clang today, which is the flagship product from the LLVM project. And that gets, lowered to LLVM IR. And then LLVM IR has two parts. Within LLVM, you've got the midend optimizer, or it's basically called the LLVM optimizer. And then you've got the backend. The backend is what actually generates or produces machine instructions. All right. The same thing. So that's the reason why languages like Rust or Julia or Go, etc., which are all based on LLVM, are so quick to be able to support all these different architectures and different operating systems underneath as well, because of this modular compiler infrastructure. That's what LLVM is. It's actually a compiler infrastructure. It provides the pieces that you need to build a compiler for your language. And the idea is, so the core parts of LLVM are you get this optimizer and you get the backend. And sorry, you get the IR and this optimizer. The backends are written by various vendors as well. And some are maintained by the open source community. But effectively, that's about what we're trying to do. You can go ahead and swap out these front ends and back ends, but you can keep these optimizations fairly, you know, uh, static. Wherein any other language that you were trying to write can make use of all of that work that has been done before. You don't have to redo this for your specific language, right? Uh, well, there's pros and cons to it. You can see the cons part, at least you can go and look at Zig because they're moving away from LLVM and pretty much building their own backend. But right now, the best project that exists today, there's only one, I guess. There's only LLVM, as far as my knowledge goes. So the idea that I wanted to actually figure out was how do you work with LLVM? How do you understand this? Because it's the thing that we're trying to look at least let me give you the superficial picture. Heterogeneous computing that I've been talking about so much, wherein how do you produce code that will run on, your target hardware? How do you do that? So the stuff in the back end that you do, which is listed here, of course, it should be listed, but I've put it there. Things like instruction selection and scheduling, etc. All that stuff will come to later. But what's important today is what I want to talk about is what is this LLVM IR? As I said, it's an intermediate representation of the same program, but it's a much lower level representation of your program. And that's kind of what I want to, talk about. So let me actually get started off by doing something very, very interesting. So let's say I showed you this program, which is this. This is the main function, and this is that. This is a typical Rust program. It's got a main function. That's an entry point. And then it's got an actual, standalone function called add. You can look at this and you'll see that this is pretty straightforward. What happens when you actually compile your code is there is a step, and I'm sort of showing that to you here. I can go ahead and actually emit the corresponding LLVM IR code that I'm going to be able to, that this particular simple piece of code is going to produce. So if I do that, it's done. I can go and check it. I've actually saved it here, but rather than that, I'll show you where this ends up getting stored because you're using cargo, right? So it should be pretty simple. So you go into the target folder where you got all the build artifacts, and then you go into the dependency section, and then you'll find, you know, an LLVM file. This is the actual LLVM, uh, you know, code that is generated, the LLVM IR that is generated from that little add program that you just wrote. All of this stuff. There's a lot of stuff here. You might be wondering, oh my God, what? Really? It's just an add instruction. The reason that's happening is because you're actually, you're not actually running just the add code. You're also doing a lot of other things. Like, for example, you will see something like a backtrace. This is all booting, the bootstrapping infrastructure that the language Rust provides. But if you wanted to actually look for just your stuff, you could do one of two things. You could just search for uh, main, and no, not this one. Now this one. Yeah, is this one? Yeah. Yes, this is the one. So this is it. This is your actual code that you've just, this is the stuff that you've written. I'll tell you that this particular thing that you see does not look anything like main because this is called a mangled main. So LLVM is going to generate a unique identifier for the main function, in which it's also going to include the main name, so that when you do have large projects, you don't end up, uh, you know, conflicting with other items that you may have included in your source code. The same thing happens over here. You'll also see add, which is, if you go look at the function, actually, it's called add. Sorry, not this one. Where did I go? Yeah, sorry. So let me just close all this stuff. So you'll see that you've also got the add function here. And that's kind of what you would be able to see here. You'll be able to see the add function as well here. So that's kind of what you should be able to see right now. Oh, wait. Yeah, so bring this back. Hopefully just stay here, man. So that's kind of what's happening. But the rest of the stuff is all this, if you want to get started with LLVM, you look at this stuff and you're like, whoa, what's all this? What's alloca? What's store, call? Pretty much, I mean, if you're looking at this, you should be able to tell that all of this stuff is probably an LLVM IR instruction. A, because it's color coded because of the theme, and B, because it sort of is a pattern you could probably tell. So yeah, you're right. These are all LLVM instructions. So LLVM itself is an intermediate has its own intermediate instruction set. And that's kind of what we use to represent a lot of the source code level concepts at this level. And then once we pull it into this level, the reason for doing this is because we want to transform this or optimize this for for a specific hardware target. So we do a number of optimizations. Optimization, what are they? A chain of them can be called optimization passes. And then whatever you get at the end of that is finally going to be handed off to the backend, and the backend produces. It also does a few things, and then it produces your machine code, right? So yeah, so as you can say, this is not going to be very clear, but it is what it is. It is LLVM IR, basically. So rather than go through this, let's actually go through something much more simpler. And that's kind of why, I looked for a crate that actually helps us write LLVM code by hand. And that's kind of what I'll come to next. So there's this crate called, let me show you what crate is that. Uh, yeah, so there's this crate called Inkwell. There's a crate called Inkwell. Uh, we can probably go to Inkwell maybe. So So let me go to Inkwell. You can see that this is basically a wrapper that exposes LLVM, you know, the LLV, that it basically a wrapper around the LLVM code base. It's actually a wrapper around the C API. There's a few things that you don't need to worry about, but the idea is Inkwell tries to provide a safe API around uh, what's usually referred to as an unsafe C API. But once you have this, once you use this, you also need to install the right version of LLVM as well. All that stuff is, you know, um, something that you already need to have. So keep that in mind. I'm not going to go into the implementation. That's fairly straightforward. Sorry, the installation part, that's fairly straightforward. What I want to focus on is how do you actually produce this code? So LLVM at its heart looks something like this. It's the way this is structured is you have, what are called translation units. So you have the module. That's why a module, in Rust as well, is a collection of items that are packaged together and they are compiled in one unit. So that's a translation unit. And then a function is the next level container. Uh, we'll see what the function looks like. And then within that, you actually have the basic block. So you can have, uh, you know, multiple basic blocks that are sort of sort of in a control flow graph. And each of these basic blocks will have instructions. The definition of a basic block is they have one entry and one exit. You can't branch in between within a basic block. So that's, the simplest way to explain this. A better way to actually talk about this is, let's say I go to, this website called the .org. It's actually a compiler explorer that's available to us, and it's available as what should call as a web-based UI. That's really amazing. Okay, so I've got Rust here. I'm using the standard. I guess this is stable Rust or something. Does not matter. Just getting to what you will see that you can go ahead and just highlight stuff, and it'll tell you, okay, which part of the source code are we referring to. All of that's possible because we're looking at this. And this is LLVM IR again. Now this is much simpler, so you could get started from here. But what I wanted to actually show you is, this. I wanted to show you this part where you actually get to see the control flow graph. I don't know how to minimize these things, so I'll just do this. Um, so you have a simple program over here that says just a square function, and it takes in one and just doubles that number and gives it back to you. So this is what your this is a visual way of looking at LLVM IR. So the same code that you probably saw as LLVM IR is in these blocks. So this is one basic block. This is the second basic block. This is the third basic block. So a collection of basic blocks that are related in using a control flow graph is what is essentially LLVM IR. All right. That's one way of looking at things. But I also wanted to talk about the Rust way of doing things. So because it's easier to get working with this stuff. You could actually go ahead and use the C API that LLVM provides to build that IR by hand. And uh, that's what we're doing over here. We're trying to build what's called a simple hello world module. Right. So I start off by saying, I'm going to go through each item because that would just make things a lot that have to cover a lot of stuff. So there's a context type, which effectively, let's go look at it. Context is the container for all the LLVM entities, including modules. So that's what you create first. And then what you do is you effectively go and handcraft each point, each thing that you need in this IR. So for example, I want you to start by saying, okay, this call instructions over here, and these are some compile time constants, and this is the actual instruction I want you to call and pass these parameters, all of this. I want to express this, and here's how I do it. I actually go ahead and say, okay, talk about pointer types, talk about the syscall type, talk about the actual function I want to create. So all of these things are available to you, and you can go ahead, let me just minimize this a bit. You can go ahead and create all of that. And finally, what you do is you use this builder uh, type. And builder is another interesting thing. It's if you actually look at the documentation as well, a builder is something that builds your instructions for you. All right. So that's the whole idea about an LLVM builder. Now, and then finally, in this case, because this is going to be the simplest possible example, I've gone ahead and because I'm using a Mac on the ARM Apple Silicon thing, so it uses an ARM 64-bit processor. Um, so you go ahead and say you've created your, your IR. Now, what you want to do is you actually want to go ahead and create uh, the executable for it as well. But even before you can create the executable, you're supposed to create the actual IR. So this is just, your in-memory representation of whatever code you've written. You need to take that and you need to produce actual LLVM IR. By that, I basically mean you're going to be generating bitcode. So you've seen this part, which is, this textual representation. There's another form in which you can, which you can acquire LLVM code. That's bitcode. That's basically the binary representation. So there's ways to move back and forth, just like disassembling. So there's an actual tool that comes with the LLVM toolchain called LLVM dis. You can go ahead and use that when you get the bitcode out and create the textual representation. So that's kind of what we're doing in the main function. We take the context, we take the module that we just built, and we go ahead and create, a place where we can store this bitcode file. And then we simply call LLVM dis, which is the command line utility that will be able to produce this bitcode, or rather disassemble this bitcode. Uh, but before we can do all that, we do the get target machine piece, and that should provide us with what we need. Uh, Additionally, I've also gone ahead one step further and tried to compile that by linking it with the standard C library that's available, right? So this is pretty straightforward. I mean, I don't even need to explain this. It'll be like me just reading out the documentation that's part of Inkwell. So rather than me do that, I just put a simple uh, hello world program together that should be able to give you the whole flow of things. That's the most important thing, to get the flow. So if you go in here, you'll see that this is the main file. This is what we're creating. And then you'll also see a bunch of other uh, files that we have. One is, this is the executable that was created with Clang. This is the bitcode, and this is the LLVM file, right? So before I actually go ahead and do that, let me see if I can simply go ahead and cargo run, just so that you guys believe me, and this isn't some basically guys don't put in line. So this is part one. So let me just go cargo run, and that should basically produce everything. So once that's done, because we're simply replacing the file, you should have seen it, but it's here. Uh, so this is the bitcode. Obviously can't read bitcode because I don't have a bitcode reader. And then the executable should theoretically work, because if I go in and just do this, where is this located? Yeah. Yeah. If I run hello world, I should probably get the output. Oh, wait. Sorry. That's not how to do that. Right? Check if the world is there. That's just a way of me trying to confirm things that everything is working. So I'm printing something out. that's about what hello world is going to do. That's what hello world is. And you can see that this is the string that I'm trying to print out. So the reason I wanted to do this is because it's easier to sort of explain LLVM IR this way and show you what it actually produces. So what does it actually produce? Let's go. I've got an LLVM extension installed for my VS Code instance, so that's why you're able to read this so clearly. So what's happening over here, if you actually sort of go back to main and look at, not this main, but if you go back to our main and look at this, you will see that uh, let's go through this a bit. So I've got a module over here, print, and let me see if I can, yeah, this should be enough, right? So this should be sufficient. So I've got my module over here, which is called print, and you'll see that here. And then if you go to the bottom, there's this thing called message. It's supposed to be a global string. That's what this whole thing is. This is private. The address does not really matter. It's constant in memory. And this is the size of that. It's 28 bytes. And you've got the character string over there. It's alignment. So all of these little details or minute details that you need when you need your code to run, all that information is present. You normally not see this in your source code because that's not how we write code, right? We expect the language to do a couple of things for us. So this is the global variable. And then this declaration comes in somewhere here where we're saying puts. So we're adding a function, which is a syscall. That's why I said. But the thing about this is a declaration because this is going to be provided by some external translation unit, which in this case is going to be libc, right? And then we go ahead and actually create the main function, which is this part. It doesn't take any arguments. It's a function type is what we say. And there's no linkage that's required because we're not, that's the whole point. The whole reason why the previous, when I ran emit LLVM IR for the simple add program previously, it generated all that because there was a lot of stuff that needed to be bootstrapped. That's not the case here. We're just simply generating some IR. And then there's a particular block of code that we're creating called we're labeling it as entry. So this is that. And then we're simply calling puts from there. That's it. So that's this part. We are going to be, inserting the call instruction into the entry block, and then we're going to return from it. That's pretty much what you get. This is the return function, by the way. This is the return instruction. So the builder is doing all the, the instructions for each block. You're able to put that together. This generates valid LLVM IR code. All right. Once you pass it to the target. So this is, this I think I pretty much overshot my time. I really do want to talk about a bunch of other things, but we'll leave it here for now. So because there's a few more things. For example, why am I talking about all this? Because the thing is, Rust rolled out its own front end, all these other pieces that they didn't want to do in LLVM IR because it's very difficult. The borrow checking part, and there's a whole bunch of things that they do in these phases. Once you get the control flow graph in MIR, you can do a lot more stuff as well. That's what MIRI uses, which is the interpreter for MIR. So a lot of stuff is actually done in the front end, uh, which means that even before you get to LLVM IR, you can do a lot of things. There's another project that's associated with LLVM IR called MLIR, which is essentially trying to provide a generic framework to do all of these transformations, right? Rather than each language build its own stuff, MLIR wants to do, the framework that you use to do all that lowering. Okay. So there's a reason we want to talk about that, because a lot of these machine learning compilers, graph compilers, etc., are sort of using MLIR to produce the most optimized version of their code for each target. Likewise, my interest is in the fact that RISC-V is a very, very important embedded target in the coming years. And there's a couple of things that we need to figure out in terms of the standard extensions to RISC-V, the way they work, the non-standard instruction sets as well that are sort of being included in RISC-V, how are they going to work? So from that context, it's something that I'm exploring quite a bit. Okay, so in probably the next few series, hopefully I'll be more regular now. I'll be able to cover things like LLVM attributes, etc. You'll see them somewhere here. For example, this is LLVM code from your if you go back to one of these streams, you'll see that I made a stream on heterogeneous computing with Apple, talking about Apple Silicon and their GPUs and all of that. Apple uses the Metal framework to write your GPU kernels, compute kernels, and then compile them. That's happening again using LLVM. Apple is a heavy user of LLVM. So the way you do that is, I've got that here. You simply use LLVM dis. So if you look at the README, this should be pretty straightforward. The way you launch your compute kernel is two steps, at least if you're doing it by hand and not some automated fashion in some iOS workflow or Android workflow, sorry, iOS workflow. You first take your Metal kernel code or Metal kernel, and you can run that through the Metal utility, and it provides a .air file. This is purely LLVM IR. That's kind of what you get here when I disassemble it. You'll see that this is very different, right? You got the target layout. It talks about NDNS, pointer, native width, then integer sizes and alignments and all of that stuff over here. And then you get into each kernel, what is the corresponding LLVM IR that's produced. And anything with an exclamation mark is actually metadata, which we can cover next time. So basically, yeah, this is what I wanted to cover. Again, don't want to take up too much time. Yeah, so that's LLVM IR, and that's something that we'll be working on, so that we understand how does source code go all the way onto your actual hardware target. What's that process for it? There's a lot more interesting stuff that I've discovered. We'll get to that in probably the next few streams. So that's it for now, and thank you.